Let's continue with some examples from section 1.8. So here we have an example where we're given a matrix A, and it's a 2 by 3 matrix, 2 rows, 3 columns. And so the associated transformation, T sub A, takes a 3 by 1 column vector and returns a 2 by 1 column vector. Now, so R3 has these standard basis vectors, and the question is, what is the image of these standard basis vectors E1, E2, and E3 under this transformation T sub A, which is left multiplication by A? And there's two ways to figure this out. One is to actually do the computation. T sub A evaluated at E1 is, by definition, you take the matrix A and multiply by the column vector E1. Here's E1, here's our matrix A, and matrix multiplication. Well, first of all, let's look at that we can do the matrix multiplication. A is a 2 by 3 matrix. E1 is a 3 by 1 matrix. So these threes match up, so you're allowed to multiply. And then the answer will be a 2 by 1 matrix, 2 rows, 1 column. And that's formed by taking the dot product of the rows of A with the columns, in this case only 1, of E1. So that calculation is done here. So here's the 1, 1 position, row 1, column 1, you dot them. 2 times 1 is 2, 3 times 0, 1 times 0, they're both 0, and so this adds up to 2. Similarly, to get row 2, column 1, what you do is take row 2, column 1, dot them. Minus 1 times 1 is negative 1. 3 times 0, 0 times 0, that's all 0, simplifies to minus 1. And so the answer to this question of what is TA of E1 is 2 minus 1. So that's the long way to figure out. The short way, as we've seen last time, is that the image of E1 picks out the first column of the matrix A. And here you see that the first column is indeed 2 minus 1, the answer that we found out the long way here. So the answer to what is T of E2, it's going to be the second column here, and similarly T of E3 is the third column. So this is, again, just emphasizing this fact. We'll see fairly often that the image of the standard basis vectors gives the columns of the matrix. Now these matrix transformations that we've been talking about, T sub A, are what's called linear transformations. That means two properties. First is that for every pair of vectors U and V in Rn, the transformation applied to U plus V is equal to the transformation applied to U plus the transformation applied to V. And why is that? Well, remember, T sub A is left multiplication by A. So this is A times U plus V. And T sub A of U is A times U. T sub A of V is A times V. And then it's a fact of matrix multiplication that I haven't ever checked. But matrix multiplication is distributive. In other words, A times U plus V is A times U plus A times V. And the second property in the definition of a linear transformation is that for every scalar or number k, and for every vector v, the transformation applied to that scalar times v is equal to k times the transformation applied to v. And why is this in this particular case of the linear transformation associated to a matrix? Well, A times the scalar times kv is equal to k times AV. Again, this is a fact of matrix multiplication that we can check fairly easily. But right now, we don't need to worry too much about it. We'll see a little bit more about linear transformations throughout the course. Here's one way we can use this fact that T sub A is a linear transformation. So suppose A is this particular matrix. Again, I just essentially chose a random matrix, and then the question is, what is T sub A applied to this vector, this element of R3. So there's a couple ways to figure this out. One that I've shown down here is using the fact that T sub A is a linear transformation. That means that if you add up a bunch of things, you can, and then apply the transformation, you can get the same result by applying the transformation to each of those summands and then adding up the result. So that's what I've done on the right-hand side here. And then furthermore, if you have a scalar in front of a vector, you can move that scalar past the transformation. Okay, and so then I've moved these coefficients, here's a -1 out in front, and then I evaluate these this linear transformation T sub A on the standard basis vectors, which are easy because, as we saw a slide ago, they're just the columns of the matrix A, and then doing the arithmetic, remembering again that scalar multiplication times the matrix, you multiply each component or each element of the matrix. So 3 times 2, 3 times -1 gives rise to the 6 and the -3 here, and so on for the other matrices, and then you add the result to get this as the answer. A second way of doing the same problem is first evaluate or simplify what this input vector is. Remember this, the question was finding the output when T sub A is applied to this vector. Let's find out what this vector is. This vector is 3, 4, -1, because remember when you add multiples of the standard basis vectors, those coefficients, 3, 4, and -1 in this case, appear as the coefficients or elements of your column vector. And so our question from the previous slide is, what is T of A applied to this column vector, where again A is this matrix, and then by definition T of A is left multiplication by the matrix A. And so here's a matrix A, we're multiplying on the left and giving this vector 3, 4, -1 as input, and well, as we do the matrix multiplication, first of all, this is a 2 by 3 multiplying by a 3 by 1. The result will be a 2 by 1 matrix. The first row is row 1 times column 1, and similarly doing the arithmetic, you get the same answer we got on the previous slide, 17 and 9. There's not necessarily one way is better than the other, it's just two different ways. The previous way emphasized the aspect of linear transformations that T sub A possesses.